So I hope that we're delivering as promised, of staying a little bit closer to the flow of the crowd than the flow of the clock. But I do want to get started just to make sure that, there's one thing that we can't ignore, and that's the flow of the stomach, because everybody's going to get very, very hungry for lunch. So just to go back real quick to just the updated agenda. Right before lunch, we're going to do a little discussion on the OpenFlow SDN concept. Right? And then we'll go, Chris will do the presentation on service provider WAN use cases. And then we'll break for lunch. That's pretty good. So for this OpenFlow SDN concepts, by the way, I'm kind of assuming, and I think all of us who are giving presentations sort of assume that in the audience there's about 20% of the crew, by kind of hallway conversation, seems pretty OpenFlow advanced. And about 20% of the crew here seems very, very OpenFlow new. And then about 60% somewhere kind of roughly in between. So I hope it's okay, if you're kind of part of the advanced crew, you might see some pretty basic stuff. If you're part of the, hey, this is the first time I'm seeing a lot of this crew, then, I hope that you find it equally interesting. Sorry, I kind of just like to walk around. So we're going to keep this fairly brief, but I think if you have questions for this particular session, please just really just raise your hand and dive in. Right? I think that's probably the best for this particular kind of grounding area. But we're going to go through some of the basic OpenFlow fundamentals, right? Just to make sure that while this isn't the full engineering, hey, here's how you get your dev environment set up. Here's how you implement your first learning switch. This is going to be a little bit more, hey, here's the vocabulary that we're using for the major functional components. After that, a few tech notes. This is sort of a little bit beyond the standard, but kind of some of the practices that have emerged in the last couple of years of using OpenFlow. So at least we have some of the vocabulary set for, okay, here's some of the kind of the harder parts. And then last, we'll go into some of the implications, and this is where we start departing more and more from actually the standard and what the standard does, and a little bit more into well, for lack of a better word, personal interpretation. So if you look at the basics of what OpenFlow, the protocol, is, the protocol is designed to go up and down between what is in general server software, but very often folks are now changing that product up above, a little the controller, and a series of networking devices that are today are generally we use the term Ethernet switch. We've seen some hypervisor switches, we've seen some routers, we've seen actually even some more creative devices down here, but the general case is a controller talking to a switch. And if you look at what OpenFlow, tightly defined, really means, OpenFlow is a protocol that actually moves back and forth in between these two. If you look at what this protocol, what's the raison d'etre for this protocol? There's a data structure that's assumed to be held in a switch called the OpenFlow flow table. And the protocol is all about setting up and maintaining this flow table. Okay, that's like the big deal. So if you think of OpenFlow, the protocol, really what you should be thinking about is, okay, how do I maintain this table? If you look at the table as a data structure, it comes in three parts. There's a match component, an action component, and a counters component. Now the match covers a header 12 tuple. The action component, there are a couple of straightforward ones, and then there are a handful of more advanced ones, but it's a fairly limited set today. And some examples here, you can see the switch with a flow table that says, okay, I'm going to wildcard all of these entries, but just match on a particular MAC destination address. Any packet that matches on this MAC destination address, I want to forward out on port 1. This is the fundamental building blocks of L2 switching. Now, it might not seem that exciting that we can use a switch to do switching, but we're getting started.
So on the match component, I also see IP source and IP destination.
Yeah.
Do we have both V4 and V6 covered here?
V4 is covered for the 1.0 stand, for OpenFlow 1.0 and 1.1. There's work going on right now around V6. Around V6, the match table starts to look different enough that it's a pretty big protocol rev. However, the implications of it are actually fairly So far, we've seen a small number of hard parts, not a large number of hard parts. We expect that to be fairly straightforward standards products. It's a great question. It comes up a lot. So, we can match on Mac and we can forward. We can match on IP and we can forward. So we can start to do a couple of things. Now, we don't have everything in place for this, right, in the OpenFlow 1.0 standard. But we can do things that look a little bit like making an Ethernet switch do, I don't even want to call it routing, but it's certainly layer 3 forwarding. And I hope this is where everybody, I can kind of see big parts of the audience just got a little bit quieter. Okay, so this is where things start to get a little bit, we start to get a little more interesting. But, we can match on anything and we can drop, so we can do simple stateless firewalling. Yeah.
Can we assume that if a hardware switch calls themselves 1.0 compliant, that they allow us this 12 people to deal with? So we use and how we differentiate it?
Dan, this might actually become more of a question for you, because the exact definition, I think, of OpenFlow 1.0 compliant is kind of I don't know. Wondering if you want to take this.
We're working on that. Every working group actually is touching on that right now. Mike Howe here in front is head of the testing interoperability working group, and they will be developing the compliance terms and specifications. But we're also looking within the extensibility working group and the technical advisory group on what a minimally compliant set of capabilities will be.
In my personal experience, unfortunately, it hasn't been quite as easy as saying, hey, do you support all the matches? Hey, do you support all the actions? Usually it's, okay, for some combination of match and action, that's not supported, or some combination of match and action is supported at a very different performance level than the rest.
We are intending for a fairly minimal subset of required compliance. And because at this point we have to allow room for experimentation, and we're certainly eager for a vendor differentiation without fragmenting the market, and that's a balance we know we have to strike.
It's a great question. So we talked a little bit about layer 2 forwarding. We talked about layer 3 forwarding. We talked a little bit about stateless firewalling. We can even do some stateful firewalling. It just takes some creativity. We'll get there in a sec. I thought that this was kind of a genius thing that got put in. A bit tricky on the implementation side, but you can actually set up a match and have that packet processed by the local switch operating system and the local switch config. It's not, you rapidly get into some very, very poorly defined areas, but this is actually an incredibly powerful construct for some networks where you're trying to do a sort of a slow and an incremental rollout, a hybrid rollout. There are a couple of different features within the protocol and within vendor implementations of it that allow for partial rollouts, which I think are incredibly important, this being one of them. There are a couple actions that I'm not going to touch on, but the last action that we think is actually incredibly important, and this is a really interesting part of OpenFlow, is the ability to match on any packet and forward that packet up to the controller for more processing. That part's important. We'll get to a little bit more there in a sec.
Before you move on, can you comment on applying to physical ports versus virtual ports?
One-ish stuff here?
Yeah, I guess you probably move into it, but the way, in 1.0 you're basically saying physical ports,
yeah.
And then beyond physical ports is beyond 1.0.
Yeah.
Okay.
At least that's the way that I think about it. So I think just a little bit of background for folks in the audience, for OpenFlow 1.0, every port was considered a physical port. 1.1 actually specifies a whole series of constructs that can be labeled as a virtual port that the controller can forward packets out. It's also an area where we're seeing really interesting innovation to say, hey, are there special features or functionality of this particular product that we can expose to an OpenFlow controller as a port? So we joke a lot about what's port 49 on the 48 port switch. It's actually a huge area to unlock really, really interesting cases and unlock a lot of the power of the underlying hardware that 1.1 takes more advantage of.
Can you maybe just repeat once again the concept of the local action? Because maybe the label is just counterintuitive.
So the local action says rather than taking an action, rather than deciding what to do with this packet in the flow table, forward it over to the local switch OS, and let the local switch OS tell you which port to forward it out on, or tell you whether to drop the packet, tell you whether to enqueue the packet, etc. So the action that gets taken is not predicated. The final action is not predicated on the flow table.
But that implies moving to software forwarding?
It depends on the vendor implementation. It's not one that's incredibly consistently defined, but in any one implementation, we found that its definition has been useful to get us around a couple of mixed mode use cases.
In terms of Ethernet forwarding, you're basically telling it what port to go out, but are you changing the destination MAC? Usually in Ethernet, you're changing your destination MAC per month.
So it didn't include in the table all the rewrite actions.
Okay.
It's usually, obviously as a co-chair working group, you're in the 20% of the audience that I'm assuming is kind of the OpenFlow black belt side.
Getting there.
A couple of the actions that we didn't mention, so in queue, so in order to enforce quality of service, you can actually set specific packets to queues. And I think as Mike just pointed out, a really important one is the ability to rewrite headers. A whole series of actions that allow you to, do very specific header rewrite there. Tell you what, let me go a little bit further, and then we'll loop back to a couple of questions because I see there are a few more. But let me just get a little bit. Keep the momentum going. If you look at OpenFlow, I think in the popular press, it's really used in two senses of the word. I mean, the first is actually the OpenFlow protocol itself. And specifically, if you look at like the OpenFlow 1.0 protocol, the entire protocol spec here is 27 pages long. I mean, it is really simple, minimal. It's very, very tightly defined. 1.1 is quite a bit bigger, but this is the OpenFlow protocol. We can all actually look to something and say, all right, there's a definition of this. But I think in the press that, very frequently you hear sort of references to OpenFlow as being much more than this protocol. And I think increasingly the term software-defined architecture is used in this area, software-defined networks. But I think of this as the architecture. If the protocol is like the x86 instruction set, then an OpenFlow architecture, a software-defined network, has all of the layers of software on top. And this is not tightly defined. This is all of the innovation that we can layer on top of the, if you extend this metaphor at the operating system level, at the application level, this is Linux, this is Perl, these are all of the beautiful things that we can build on top of the x86 instruction set. If you look at, I kind of think that this is, so if we exit out a little bit from OpenFlow, the standard, right? This is going to bridge a little bit more into the world of, what are we currently seeing in open source and in some of the beta products out there? I think thanks to some of the really visionary work that went into the early open source products, we kind of developed this three-tier model for OpenFlow. And I think you'll find a lot of people who kind of use this in their heads when they talk about an OpenFlow or a software-defined networking architecture. The first layer is the switch hardware. I think it's pretty obvious to everybody in this room that you need Ethernet switches to build an OpenFlow network. But what's typically in this, in the protocol spec called a controller is generally in practice we find split into two layers. There's this controller layer underneath that generally, and I'm kind of saying generally across the commercial products that I know, and certainly the 7, give or take, open source implementations that I've been looking at. The controller generally does a lot of kind of marshalling of the hardware resources up and down. But if you think of the traditional control logic, something that we would think of as, hey, here are the features of this network, or the features of this network device. You find those generally in this year's applications that are independent or semi-independent from the controller sitting on top. So I think when you ask the question, okay, what does OpenFlow do very often, I think the best answer is to say, well, here's what the controller can do, here's what applications can do today, and here's what a couple of new applications that you could write could do. I think just one more on the technical side before we go into implications. I touched on before this real importance of the match and forward to controller action in the switch. It's really important for a number of reasons, but I think that if you wrap them up, you wind up finding people talk a lot about two very distinct models under which you can build OpenFlow applications and architect OpenFlow-based networks. You find one that's a proactive model, which is, okay, as soon as the switch connects to the controller, or if some kind of external event happens, the controller is going to push the entire flow table state down to the switch. All right, this is called a proactive model. And if you look at OpenFlow, there are people here who have been in the OpenFlow community, long. I've been involved for 2 years, and certainly when I first got involved, this was a real religious debate. And I think as we've learned a lot from more of the implementations out there, I think we're all finding that the right answer is somewhere in the middle. The proactive model is that the switch, as soon as it connects to the controller sends down the entire flow table state. The second is actually using that match. Okay, forward a packet to the controller. The switch starts empty. A packet comes in. The switch doesn't know what to do with it. It sends it up to the controller does some processing, and sends it back down with the appropriate flow mod. So that all future packets that way, all subsequent packets, follow that same path. This is part of why when people ask questions about the performance of an OpenFlow network, they can be really, really difficult to answer. Because it really is entirely dependent on which applications you're using and how those applications were built. Does the application run an entirely proactive model? In which case all of the packets should go at line rate? Or is the application built in a reactive model where the first packet of every flow is going to see some amount of latency and then all the subsequent ones are going to go at line rate?
Or first several.
Or first several. But this winds up being a really big source of confusion and debate out there.
Going back one slide. Looking at the commercial products and the open source, how similar is the interface between these applications designing the functionality and the controller? Is there an API forming up at this point, or is it everybody different?
The open source ones, depending on which, there are a couple of open source ones that are getting a little bit further along, but most of the open source ones are really thin wrappers around the OpenFlow protocol itself. So it says the application registers for a packet in and then can send flow mods out. The more advanced open source ones have a little bit of a higher layer of abstraction. And right now it's the commercial ones that are tracking a much more powerful layer of abstraction. I think over time, a lot of the commercial R&D, as it gets increasingly successful, is going to migrate over to open source. So right now, I'd say that's probably part of kind of commercial secret sauce, that over the next 2 years, the best practices are going to filter down to open. If you look, here's sort of the final tech note before I go into at least my personal view on implications. Distributed systems programming is really, really hard. I think I'll find a few. Distributed systems programming is really, really hard. Distributed systems programming on the types of primitives that you get from a typical network device in terms of being able to edit the config is even harder. OpenFlow, I think the reason that a lot of people look at this and say, my gosh, this is so much easier to work with, is because as a central, if you think of the model of a single controller and a whole bunch of switches, it's really, really an easy model to work with. In practice, that's not quite the case. You still have a distributed systems problem because we always wind up seeing multiple controllers so that switches can fail back and forth between controllers. So it's still a distributed systems problem, but I'd argue that most, when we see very common builds that are looking like an OpenFlow controller for every 100 switches, every 500 switches, every 1,000 switches, in some cases a few, in some cases more, the level of distribution and the primitives that you get underneath make this a much easier distributed system to program on top of. It was sort of built with a distributed systems mentality in mind. So not quite a centralized system in practice, but not super distributed.
So far, we really don't have a definition for a switch talking to more than one controller. We don't really have a definition of controller to controller yet. So
yeah, nothing standard.
Yeah.
I mean, so far that we've seen vendor implementations that have both of these. But yeah, nothing standardized quite yet. So yeah, I didn't raise your hand a couple of times. I'm sorry.
I have a couple of questions actually. It's accumulated. So if you go back to these slides, one forward. Yeah. I think I lost it. So let me just describe the question.
Sure.
So you said this is mostly a forwarding system, right? So during the forwarding, is it possible to
So that was the rewrite action that we were talking about very briefly with Mike. So a rewrite across a number of headers is supported action in OpenFlow 1.0.
What about modification of the body, the payload?
So far, nothing in the standards, and I've never seen an implementation that let you do that. Not to say it wouldn't happen in the next rev of the standards or in the next rev of implementations. These implementations are coming fast and furious, but I haven't seen it yet.
What about controller-to-controller communication?
Nothing standard. We have in the open source. We've seen a couple of sort of let's say provisioning style and provisioning speed controller communication. In the commercial product, we're seeing actually really advanced controller-to-controller communications in order to support all kinds of different failover mechanisms.
So with this protocol support, we say, for instance, at line rate, I want to use encryption or compression or something like that, line rate, right? And would OpenFlow have some kind of an action which would be able to, which one can describe as render-specific actions or?
I think the interesting thing is that and actually, if you have some thoughts here,
Why don't you say that it's generic enough that you could forward it from, once you apply your match and then you decide on your action, you could forward it to a virtual interface that could be taking some other action. That could be specific to what your hardware is able to do. So I don't think that's actually a component of the OpenFlow definition. What we're kind of saying is OpenFlow is how to separate the control plane from the switch, but then you have a standard set of operations that you're performing. But then what you're doing with your own product and what it's capable of is really vendor specific or specific to the application of that product. So you're not saying you can't do it, but it's just not part of the OpenFlow standard at this point.
we've seen some actually really cool, early or alpha level implementations of, okay, a 48 port device, port 49 is one specific type of tunnel, port 50 is another specific type, port 51 could be accessing encryption.
Just one last one. So one of the slides was the religious slide, in which you had something to do with reactive model. So is that what is learning? Is that what a reactive model is learning? Is that what? Is that what? Oh, thanks.
Hold on. If other people can't always hear you in the rest of the room. No, it's for the.
Okay, going to the current slide, I was wondering if those buckets or containers that you showed, do you expect homogeneous switching deployment in each of those? Is that just state of the art, or is state of the art is also that what you can find over there is very heterogeneous, and also what is today the size of each of those buckets?
On both, it's a completely vendor dependent. If you look at some vendors right now, and again, this is, I'm going to start, please caveat, this is personal opinion from being one of the vendors. Let me be very honest and transparent about that. We certainly see some controller vendors trying to specialize in homogeneous networks, and others very specifically making it a competitive advantage to specialize in heterogeneous networks. So it's absolutely controller implementation by controller implementation dependent. And specifically, I'd say it's part of it is the controller implementation, a lot of it is the applications implementation on top. Yeah. And in terms of size, we certainly see the state of the art. The expectation is a controller should be able to, in a load test, handle in the 500 to 1,000 switches range. In practical terms, we're usually seeing sort of somewhere around either one per row or one per couple of rows types of deployments. But I think some of that's also because we're fairly early days still. These things will grow, and we'll kind of figure out what the relationship is between controller scope and pod scope. Thank
you. There's this QBH standard talking about virtual pod extension. Does .1.0 spec also addresses the compatibility between the two protocols? The interoperability between the two? Yeah. So virtual pod extension and OpenFlow spec 1.1 talking about virtual ports.
Yeah, sure. I mean, the relationship between QVH and 1.1, or more specifically, I think more appropriate would be the 1.2 question would be orthogonal in 1.0 and 1.1. But let me again kind of leave it to the standards body crew to talk about the going forward.
OpenFlow should improve the usage of network and improve the transparency of network, and should be a good idea to prevent header rewriting rather than encouraging them.
I think it's kind of more of a personal, I mean, I guess my personal opinion is that header rewriting to achieve certain very specific use cases is actually a great thing and can be more effective than tunneling sometimes, but it's very, to be honest, in the scope of pilots and very, very early production builds that I'm looking at, it's very much some people love the idea of doing header rewriting because we can actually create some clarity in the headers and we believe actually make the network easier to debug. Whereas others certainly have a much more tunneling-centric view and say, hey, no, we want to tunnel everything. I think the right answer is OpenFlow will wind up having to support both, and it'll be up to a mix of applications to figure out how they want to use those resources, then up to network architects to say, hey, no, I think my network is cleaner and easier to debug if I do a tunneling everywhere approach, versus I think that my network is actually cleaner and easier to debug if I do a rewriting approach. Same heterogeneity that we see in networks today. So I think we started out, I think, a little bit close to the standards, and then a couple of notes that were a little further from the standards and a little bit more on, hey, what's kind of the state of the art out there. Ooh, this is now going to dive even further forward and say, hey, here's a couple of the implications, at least that we're seeing out in the market for, why is OpenFlow, what's being built on top. The first that I think a lot of people glom onto is this immediate sense of, okay, wow, I can take a server, I can take a bunch of switches, and by just changing my server software, I can change those over from firewalls to routers to different switch topologies to load balancers. And I have immense flexibility that runs at software speeds without changing the hardware in and out of my network. All right, so I'll just say that this is, well, I'd say the best thing I can do is go look at some of the demos. The demos this evening, I think, will show many demos that are going along this line of thinking to say, hey, this is one of the really powerful implications of OpenFlow. Is this hardware once, and then I can rev after that with different software modules. It's just an exciting area for demos right now, and for some of the very, very early, we've seen pilots in this direction. I think the second really exciting implication that, at least certainly that we see, is this idea that, okay, hey, if you believe that you can actually run a network by having a controller layer and a series of applications, well, the control layer is a really good layer to put in a level of network indirection. So when we hear about network virtualization or multi-tenancy, this is a major theme for OpenFlow that I think you'll hear repeated throughout the day. I give a ton of credit to Rob Sherwood and the early work on FlowVisor that really kind of pointed us down this direction on the academic side and the open source side and the early research before this started being commercialized. But I think if you look at, again, I point to the demos, point to what you're going to hear today as the needs. This is a big part of the, in my view at least, what's driving the state of the art forward with OpenFlow. Last is network automation. I think, Eric, thanks to your question, certainly heard it come up earlier. Can we build a saner platform for large-scale network automation with OpenFlow? And I'd argue absolutely yes. I mean, if you look at, to me, this would be sort of a sane kind of, this is sort of what you would want to do if you're trying to automate a network operation at very, very large scale. This would be, it is a pure kind of software writer's perspective. I would imagine this is how you'd start. And if you look at the real nightmares, okay, update the state of a network slice. Let's look at what's really involved. I mean, at least when I've had to untangle some of these things myself, some of which I wrote and some of which other people wrote. This means that you have to actually compute which devices are going to be involved. Right? That alone is actually really, really hard. That means that you have to figure out how much is config and how much is soft state that you need to somehow change or edit or delete and relearn. And third, you need to figure out, okay, is the physical topology still matching the assumptions that you had underneath when you first wrote the script? That's like 3 really, really hard things to do in this first bit. Right? Okay, now say you got through that. Now you have to actually double check to see whether or not the changes to the state that you intended are actually working. Again, that's actually really hard to get even close to right. I mean, that's hard mental challenges, I think, for folks who are trying to do this manually, and the idea of automating this is actually extraordinarily difficult. This is a pretty, I'd say the first actually bumps into very legitimate, hard and impossible to solve computer science problems, to get a general case. The second part is just hard very practically. And then the third piece being to, in a sort of transactional way, or network-wide startup traffic, so that you don't have different parts of the network starting at unexpected times before you're actually done with the script. This is also an engineering challenge that's a much larger distributed systems challenge with traditional networking devices than you'd expect. So bringing up the ports in the right order actually turns out to be pretty tough. Last of all, if any of things, so there are some error cases that you catch, there's some error cases that you don't, you just want a blanket catch-all and rollback. And this part is really, really, really hard. So if you look at, hey, can OpenFlow provide a same platform for much larger scale network automation than we've done before? Elbow grease and know-how can get you through a lot of this stuff, but there are hard computer science problems here underneath. Peter.
I'll accuse you of slightly making an unfair comparison because you're saying network management for a manually configured network is very difficult, whereas on OpenFlow it would be simpler. I mean, there's an intermediate step that's at least possible of having a generated network of a conventional form as an intermediate step as opposed to jumping to OpenFlow and then asking what about the network management of a network that was machine generated rather than human generated.
So if you do, because we used to fool around in kind of my past life at Cisco, we used to fool around a lot with saying, hey, look, if we can get a central point that actually generates all network config and get any human touch out of it. The hard parts that we typically ran across, not typically, there were a lot of projects that were going on with this. How much of the physical topology can you know a priori versus how much is learned, and how is that going to affect the actual network configs that you generate? Right? Even just like, hey, getting a same topology sense. After you've generated the configs, how do you bring them up in a transactional state? So how do you get enough of the devices to say, okay, yeah, we'll accept this config as the first phase, and then as your second phase of your commit, okay, great, now turn it on. But right now, actually, across most network devices, that's bundled into one step. So you fire on the config, and it's changed, and you have no opportunity to say, hey, let me do a dry run across a couple thousand devices before I commit. So having come from a place earlier in my service provider career where we did that, and that was in the internet core, and that was very static infrastructure. I mean, I didn't put new traffic engineering switches in every day or new configs in every day. The number of scripts to do that right for a constellation of probably 1,000 routers and 200 traffic engineering switches, which is smaller in scope than most cloud infrastructure today, was somewhere on the order of about 500 scripts that had to be run in various combinations and with various config files and checking, and it was a major engineering effort just at that scale. Now today it would probably be less, there's more commercial stuff out there, but it's a non-trivial problem when if you make the assumption that you know what the topology is, that assumption turns out to drive what assumptions normally drive.
Somebody else?
Okay.
So again, so in most cases it comes back to the capability of TCAMs. So will this fit into TCAMs or not? And I'm not seeing how OpenFlow will solve the TCAM problem, especially if you have multiple vendor switches and multiple types of switches. So they all have a different way to deal with TCAMs, and the problem is always the dry run problem. So how could I do a dry run with OpenFlow? How could I have multiple slices and figure out if I will exhaust my TCAM or not? So how will I deal with this?
So I can take that. Well, I think there are two pieces. First, I think there's a frequent assumption that 100% of OpenFlow is basically implemented in a switch TCAM, and I think the answer underneath is we've actually seen a pretty larger variety. And certainly as we go to multi-table, then the idea that OpenFlow is just controlling a TCAM starts to drop out more and more. The second piece is that at least we have a somewhat deterministic model that we can reason around. And you can reason either at the switch level or at the controller level to say, okay, here's my model for what the current state of the switch is, and that's a limited enough set to be able to run a basic test against it. So that you can begin to model and actually simulate a lot of this stuff before you begin to connect to the switches. Then when you do begin to connect to the switches, the model state is actually small enough again that you can check and sanity check.
You're somehow, you told us you're somehow between the learning model and the dynamic model and the static model. So for the static model, this will apply, but then the dynamic model, so I don't know how many entries the switch already had learned. So if I want to reprogram another slice, I would easily run out of TCAM space. So it's just a question, so how will we interact with this? Say, or maybe we have a different approach besides using TCAMs and whatever. So it's,
but I think there's if you're getting the meta question right, it's what happens when you actually exhaust the hardware resources of the network.
Yes.
You know, and I think I hate to beg off the question, but it's a little bit like put one too many VMs on a server. It really will slow down. There's kind of, we can't create hardware where it doesn't exist. I think you'll find that in a lot of across all of the open source implementations, they deal with error cases around what to do when there's not enough hardware resource in very, very different ways. And I think that's actually a very active area of the kind of state-of-the-art network of open flow networks. If I look over the more commercial models, that's where I think, since these things kind of have a little bit more larger scale networks banging against them, that's where you kind of run into folks who have thought a little bit more about how to solve this problem and what the appropriate thing to do is there. In some cases, you can re-optimize around it, and we're seeing very, very active work there. I'd say, hey, I don't want to make this decision here. Let me move this decision to a point where I have the appropriate hardware resources, very often the appropriate TCAM space, if you will. And others that say, hey, look, you're trying to do something with your network that your hardware doesn't support. Please upgrade. Just again, this foreshadows a little bit of my talk. Again, similar case, when I ran service provider networks and you run out of capacity on links, if I'm letting the routers independently make decisions about that, they will usually make poor decisions about that. If I have an overall global view of the network, I can make decisions that say, yes, I'm resource exhausted in this locality, but I have excess resources over here. So it's all what Kyle said. If I have a controller that has that larger state view, it can say, okay, this switch is exhausted. Are there things that I can move on that switch to somewhere else to make more use of the resources? And that's hard to do when every switch or every network element has its own view of reality. So I think that's one of the things where actually controller helps in this case. I think on that note, that was sort of the last set that I had. So we've been taking questions throughout. I think maybe we should just take a break here for 2 minutes while Chris gets his slide set up. Again, I just asked, we're running a little bit tight on time vis-a-vis lunch. So rather than a big 15-minute break where everybody walks outside, if you wouldn't mind again, just say a quick